radical functions. We did our warm-up already, and then we remembered to record this. So the standards we are covering today, we are going to be graphing square root and cube root functions. Okay? The rest of these we've covered in other lessons. We are also going to be transforming functions of the square root and cube root variety. Okay? And we are going to experiment with cases and illustrate an explanation of the effects on the graph using technology. We're also working on recognizing an even and odd functions from their graphs. To do all this, you need to be able to make sense of problems and persevere in solving them. You need to construct viable arguments and critique the reasoning of others and use appropriate tools strategically. So here are our goals. We want you to be able to both graph and analyze square root and cube root functions. So that's where we are headed today. Okay, first of all, a radical function is a function that has radicals in it. What do radicals look like? Well, they could look like square root. They could look like cube root. So something that is an nth root, right? With variables in the radicand. The radicand is the stuff under the root, right? So something in there, right? That's a variable. That is what a radical function. One of these types is a square root function, which is a function that contains a square root of a variable expression. So the basic form of this is y equals square root of x, right? Other types of basic functions are y equals cube root of x, y equals fourth root of x, right, et cetera, right? And I believe we are on page 323 for all of this. 323. So let's now look at the square root function, okay? I'm going to put this on Desmos as we talk through all these concepts so I can animate things. Okay, so the first thing talks about the domain of this square root function. We see here, as we go to the left with our tracer here, that the lowest x value we get is 0. So where does my domain start? 0. And it goes all the way to positive infinity, doesn't it? Everybody good with that? What is the lowest y value I get? 0. And then they all increase from there to positive infinity. So my range starts at 0 and goes to positive infinity. My x and y intercepts are the same point, 0, 0 here. Okay? 0, 0. My end behavior, I have a definite starting point, so I can't take and go all the way to left to negative infinity with my x's. I can only go to 0. So as x approaches 0, f of x also approaches 0, right? As x goes to positive infinity, or as x gets bigger and bigger, what's happening to the y's? They're getting bigger and bigger as well. So f of x is approaching positive infinity. Also, as we move to the right, my function values, the y values, are getting bigger and bigger, so we are an always increasing function with this parent function y equals square root of x. All our y values are positive for positive x values, and there's absolutely no symmetry, right? None whatsoever. Okay, when we are looking at the square root function, and we're trying to make transformations of that square root function, you see as I'm moving everything back to its original position. I'm going to also graph the point h comma k. Okay, I'm going to label that. And you're going to see, as I move h, right, what's happening to my function? It's moving. As h gets bigger, my function moves to the right. Now, when I'm looking at the graph of this function, this would actually look like, as it stands right now, y equals square root of x minus 4, right? Okay, so when my h value is positive, it looks like an x minus under that square root, right? Because there's a minus in my original format. Okay? And then when k gets positive, it moves up. When k goes negative, it moves down. And we can see that starting point is that point h comma k. Because I can just tell it, hey, graph h comma k, and you see where that starting point is all the time. So it's like a handle for our function where when we change h and k, that 0, 0 point is the point we're looking at for the start of our function. Right, Nevaeh? Yeah. Awesome. Now, what does a do? Pardon? Yeah, it's our vertical stretch and compression. So when a is 2, right, 0, 0 doesn't change, right? But if I go over 1, instead of going up 1, I'm going up 2, right? Instead of going over 2, instead of going over 4 and going up 2, I'm going up 4, right? Okay. Now, this is kind of weird. Let's change. Oh, I can't change it on that. Let's change this back to the original function because I want to show you something about the proportions of this so that we can graph this quickly without having to put a lot of calculations into it. I need everybody paying attention. There's no need for computers out right now. I want everybody to learn this. It's in a what? So you're not even doing it in my class right now? A test in my class? Okay. Normally, when we have a square root here, okay, my y values are what happens when you take a square root, right? So my y values are going to be numbers like 1, 2, 3, right? Okay, for the integers, okay? My x values are going to be the numbers. Okay, so it's like x squared is backwards, right? If I square 1, I get 1, so the square root of 1 is 1. If I square 2, I get 4. So the square root of 4 becomes 2, right? So usually I can go over 1 up 1. Over 2, up square root of 2, right? Over 3 up square root of 3. Over 4 up 2, because 2 is the square root of 4, right? Over 9 up 3, right? So we're swapping what we would normally do for an x squared. Right, Nick? You with me? No? Let's get with me. Because this is the easy way to do it. Otherwise, you're going to have to do a lot of calculations. Okay, so when my a value becomes 2, here, I go over 1 up 2 instead of over 1 up 1. Great, that works. Over 4, not up 2, but up 2 times 2, which is 4. Over 9, up 6, right? Instead of 3. And if a was negative, what happens? We have a vertical reflection down across that x-axis, right? So over 1, down 1. Over 4, down 2. Over 9, down 3, right? And if a was negative 2, then those numbers, dang it. Over 1, down 2. Over 4, down 4. Over 9, down 6, right? You with me?
Yep.
Okay. Now, normally when I teach transformations of functions, we have a b value in there as well. And there's no difference with this. So usually what I would teach would be equals a times the square root of b times x minus h plus k. And you're going to see in the very first problem, they give us a number as a coefficient of x. Okay? And what I like to see is us factoring that out. Okay? Because then you're going to really see what your h value is. Okay? So here's our example 1, page 324. So we want to identify the domain and range of f of x equals square root of 2x minus 6 plus 1. And then I would like to graph that as well. So we see here we have a value in front of x of 2. So I'm going to factor that out. If I factor out a 2, I'm left with x minus 3 plus 1. Everybody with me? So this is our function. This is an equivalent function. Okay? And we can see my h value is 3, and my k value is 1. So when I'm going to graph this function, I know where to start. And it is going to be okay, so remember this is the format we're looking at. So when I see a number here, that's my h, right? When I see a number out here, that's my k. And h comma k is the beginning of my functions. So I'm going to go over 3 and up 1, right? Okay, and we know that it's just going to kind of go like that. Now, I'm not going to address what 2 does here because that's not part of the learning, even though they gave us a function like this. But we can tell about our domain. The domain is the set of all x's such that x is greater than or equal to 3. And my range is the set of all f of x's such that f of x is, what's the lowest y? 1, greater than or equal to 1, right? So this number here is my h, that number there is my k, and unless I've got some reflection going on, right, it's always going to be greater than or equal to's, right? Okay, now the book did it the algebraic way. They said, hey, the domain is going to start when the stuff under the square root is greater than or equal to 0. So they set that greater than or equal to 0, solved, got x is greater than or equal to 3. Then they said, oh, hey, I can find the y value by finding f of 3, and then I got 1. I didn't have to do all that, did I? I just had to do one factoring and read my function. Can you do it either way? Yes. You pick which way your brain likes best, okay? Next, we want to graph g of x equals negative 3 times the square root of x plus 1 plus 2, and identify our domain and range and describe how it is related to the graph of the parent function. So when I'm looking at g of x equals negative 3 square root of x plus 1 plus 2, and we know that we're dealing with g of x equaling a square root of b times x minus h plus k, right? This negative 3 is my a value, right? What's my h value? This has a minus in it. Negative 1, so it's opposite. And then k is 2. Okay? What does the k equal 2 do to my function? What transformation does it create in my function? Yeah, it goes up 2. Okay? Stuff under the square root happens with x's, so what does h equal negative 1 do? Yeah, left 1. Okay, when it's negative, it goes left or down, right? Those are the negative directions. Inside my root affects x's, so that's going to be right, left. Outside my root affects y's, so that's going to be up, down. Then a equals negative 3. There's two parts to this, the negative and the 3, right? What does the negative do? Yeah, it's that flip down across the x-axis, right? So reflects down. And the 3 is a? Stretches it. The y values are 3 times as high as they would have been normally. So this is vertical stretch times 3. So the y values are 3 times higher than normal. Okay? So my domain is the set of x's such that x is, maybe not. Let's take a look at this graph. I should have left room for this graph. So we're going left 1 and up 2. I'm going to put this here. So that negative 1 comma 2, right? Actually, I think I want to move this up a little bit. There we go. So now, instead of going over 1, up 1, we're going over 1, down 3, right? Instead of going over 4 from the vertex and down 2, we're going 2 times negative 3, so down 6, right? Oops. So that's my square root function there, right? So now, what do we know about the direction of my x's? Is it greater than or less than 2? What sign should I put in here? Yeah. Well, x's are greater than, or sorry, it's 1, isn't it? Getting my y's. 1, negative 1. It's greater than or equal to, right? Range. Set of f of x's such that f of x is less than or equal to 2, right? Those go down, not the domain. Okay? Okay, so the maximum of this function is negative 1 comma 2, right? And because f of x equals, we did the a as 1, we did the vertical stretch and right and left. Okay, I think we've covered everything. We're going to skip example 3. And we're going to look at this one. Actually, we're going to skip example 4 too, because we're not doing any radicals with our homework. Yeah, we're not doing radicals. Okay. Next, cube root functions. Actually, I want to do some more square roots. I think we haven't done enough of this. We need more than just 2 problems. So if you have some room on your page, let's take a look at we're gonna do y equals 2 times the square root of square root too big. Square root of x minus 1 plus 3. Okay? So what is my h value? What is my k value? What is my a value? So a is always that first number right after the equal sign, right? Yes. That was for finding the domain and range. Yeah, that's just setting the stuff under the square root equal to 0 and solving. This is an easier way. Do you like calculations? Okay, well this is the way without calculations. So this is my a value, right? That tells me vertical stretch, right? And my h value comes next, right? So h is just 1. My k value is last, so that is 3. So my start of my function is h comma k, 1 comma 3, right? And then I'm going to go over 1 and up 2 to get my next one. And over 4 and up 4. 2 times 2, right? To get my next one, and boom. There's my square root function, right? So my domain is a set of x's such that x is my range is the set of f of x's such that f of x 3. Okay? Is that making more sense now? So if my function was just y equals square root of x minus 1 plus 3, it would have started here and gone like this, right? And my y values are 2 times higher than that because of this 2. Okay? You with me on that? Okay, then I'll animate it. Okay, so I'm going to graph x equals h. I'm going to graph y equals k. Okay. Now I'm going to have just regular square root of x, right? I'm going to move it over 1 and up 3. Okay, everybody with me on this? You see how when we do this, I put these little vertical and horizontal lines in to kind of give you a fake xy axis. Okay? See how I'm still from that fake xy axis going over 1, up 1, over 2, over 4, up 2, over 9, up 3, right? Okay? So this is with an a value of 1. Watch what happens when my a value is 2. Okay, now from that fake xy axis starting point, I'm going over 1, up 2, over 4, instead of up 2, it's up 2 times 2, which is 4. Over 9, instead of up 3, it's up 2 times 3, which is 6. Okay, so the y values are all 2 times as high as they would have been normally. Everybody with me on this? Okay? It's not difficult. I'm trying to teach you the way that you don't have to plug in points, right? But you have to know all this stuff, right? Okay? I'm going to go over 4, up 2, over 3, or over 9, up 3, over 16, up 4. See how that works? It's kind of the x squared values swapped. Does that help? Nevaeh, are you better with this? Okay. Well, we're going to have to schedule some time together then. Any other questions? Okay. Now we're going to go on to cube roots. And these are radical functions that contain the cube root of a variable expression. So we're going to change all of this to cube roots instead of square roots. Okay, I've got to redo this radical expression. Bring a back down to 1. Okay, so this one's going to be a little bit different. And because when you cube a number, the values get so big so quick, there's very few numbers we can actually look at here. But we do see that as I move from left to right, I don't have a start or stop for this function, do I? So my domain is all real numbers. My range is all real numbers, right? Yay! Odd power functions are nice. We do see we have some symmetry with respect to the origin, right? So this is an odd function, right? If I snip it here at the origin and take the right half and rotate it 180 degrees, it lays directly on top of that left half of the function, right? Okay, that's origin symmetry, an odd function. Okay, where the f of x values here are the opposite sign of the negatives, right? Okay, so this still works the same way, h and k. We move it over and up, my function's going to move. But what you're looking for, h and k here, is to be right here at this point where it changes from concave up to concave down, and that is known as an inflection point in math, okay? But this point, this inflection point, is going to be the handle of my function, okay? So when I move it up, down, right, left, it's going to be with respect to that inflection point. That's where your kind of fake xy axis is going to be, right? Okay? That's the starting point for what we're going to consider. But the nice thing is I can look at how much I go up and over and do this opposite thing on the other side of that inflection point. So if I go right one, up one, I'm going to go left one, down one. If I go right 8 up 2, I'm going to go left 8 down 2. Okay? Make sense? Okay, because 2 cubed is 8, the cube root of 8 is 2, and that's the next integer value for our y's, right? Is to go over 8 up 2. Make sense? So there's really only 5 points that you'll probably be able to put on any graph. That is negative 8, negative 2, negative 1, negative 1, 0, 0, 1, 1, and 8, 2. Right? Make sense? So when our a value changes and gets bigger, right, we would go over 1 up 2, over 8 up 4, right? Or left 1 down 2, left 8 down 4. If we have a negative value here, say we have negative 1, see how we go over to the right 1 down 1, to the right 8 down 2, and everything just kind of flips. Make sense? So this is, cube root functions operate the exact same way, they just have slightly different proportions because cubing functions. Phone's away. Okay, we can see this is an always increasing function. We are positive for positive, y values are positive for positive x values, negative for negative x values. We introduce that form. I'm going to graph these in a different order. We're going to start with problem B here. We're going to graph each function and then work on our domain and range. Just trying to make sure I've got enough room here to put this in here. So I've got the cube root of x plus 5. What's my a value here? Yeah. 1. And my h value? -5. And my k value? 0. There's nothing over here, so k equals 0, okay? So I'm going to start, my inflection point is going to be at -5, 0, right? Which means I can go to the right 1 and up 1, to the right 8 and up 2, to the left 1, and then, oh, that's about all I can fit on my function, right? Okay, so what is my domain? Yeah. What is my range? All real numbers. So these odd-powered roots are nice. All real numbers, nothing crazy about it. Okay? This next one, actually, I'm going to just... Just going to erase this. Okay. This one is kind of weird because these two terms are backwards of each other, right? So this is going to be the cubed root of, let's do those roots so long. We're going to factor out a -1 times x minus 4 plus 1. When we factor out that negative value, that allows us to see our h and our k, doesn't it? So my h is 4, and my k is 1. So I'm going to go over 4, up 1, and that's my inflection point. Now, this -1 is a b value of -1, right? Which is going to flip it side to side. So instead of looking like this, it's going to look like this, right? So not that, it's going to be this one. Flipping it side to side has the exact same effect in this case of flipping it top to bottom because it's an odd function. So I'm going to go over 1, down 1, left 1, up 1, left 2, 4, 6, 8, up 2, and we're going to try to draw our function. Okay. Domain and range? All real numbers. Okay. Last one is kind of a weirder one. Oops. Because we've got an a value that's different, right? So here my a value is 1/3. So this is vertical compression, right? Because my y values are 1/3 as tall as they would normally be. And h is 0 and k is 0, so we're good. So instead of going over 1, up 1, we're going to go over 1, up 1/3. Instead of going over 2, 4, 6, 8, and up 2, we're going to go over 8, up 2/3. And the same thing in the down region. Very little vertical change in this function. It still keeps increasing to the right and decreasing to the left, but it's just not very tall, huh? It's going to take it a while. Domain and range, all real numbers. Okay. So we are moving on to example 6 now. Okay. So we've got example 6, says examine P of x and Q of x. And Q of x is on the graph already. So let's put P of x on there so we can kind of examine them and compare our features, right? So where is my h comma k? Kennedy, what do you think on this one? What's h and what's k? Yeah, k is definitely 0. Kennedy, what do you think the h value is? So remember, we're using a times the cube root of x minus h plus k. Now can you tell where your h value is? 6. So 1, 2, 3, 4, 5, 6, comma 0. Oh, hey, they have the same starting point, don't they? I'm just going to put this in pink so it's a little bit different. Right? If I go over to the right one, am I going to go up or down? If I go right 1, am I going to go over or up or down 1 or 2 or something? Down by 2, right? Because of this negative 2. So this value, this point is the same, and then but this, I'm going to go to the left and then up by 2. So this function is going to kind of look like this, right? Okay, so what do you see about P of x? Well, it's a cube root function. What about Q of x? What type of function is that? It's a square root function, right? Because it has a definite start and stop. Okay, so we graphed. Hmm?
Oh no, last dinner she had the.
For what?
I was asking her.
Oh, I haven't passed them out because it's not review day yet. Oh, well, I might have extra copies up here later. Okay, so because P of x is a cube root function, my domain and range is all real numbers. But Q of x was a square root. So its domain was all the x's bigger than 6 and all the y's smaller than 0. Really? Was that? Yeah, that was 0. Yeah, okay. They both had x-intercepts of 6. P of x had a y-intercept, Q of x did not. They're both decreasing functions. Okay? They're both negative for x is bigger than 6, but P of x was positive for x is smaller than 6. And then as x gets smaller and smaller, P of x got bigger. But for both of these, as x gets bigger, our y's get smaller. Okay? And then we had this one. This one's a good one. Here we're going to look at the graph of the function and try to write the radical. Okay, first of all, what type of function is this? It's a cube root. So y equals cube root of something, right? Where's my inflection point here? Yeah, -3, -4. So h equals -3, k equals -4, right? Okay, looking at this. Remember, we have a fake x-axis, fake y-axis. If I go to the right one, how many am I going up or down? Up 2. So what does this mean for my a value? It's 2, right? So what comes right after the equal sign? The 2. And then x minus my h, which is negative 3, and minus k. So this is going to look like 2 cubed root of x plus 3 plus 4, or minus 4. Meant to write a 4 there. Okay. There's another check problem for this. I'd like you guys to try that one on your own.
The negative 4 is because that point there, the inflection point, is the point negative 3. Because it's the full squiggle instead of half squiggle. Right? How do I know it goes back down? See. Okay, the graph was given to me, right? I didn't have the graph. So let me understand the question. You said, how do I know it goes back down? You're having to write the equation. We're giving you a graph, and we're saying, what's the equation for this graph? So I see it's a full squiggle, so that's cube root. Find the inflection point, right? Find that middle point. That helps me with my h and k. And then I go over 1 to the right and see, do I go up? So a is positive. Do I go down? So a is negative. How many? What is my a value? Okay. So you got it? If you could be more specific with that, I might be able to help you. When you just say I don't get it, I don't know where to start. No, I need to be able to, I can't read your mind. If I don't understand where I lost you, I can't help find you. And then what you take tests on that thing? Stop. Bro, I do.